fundamental theorem of calculus, where we connect antiderivatives to area constructions. From the last video, we did the area construction of Riemann's sum. Fundamental theorem of calculus says, look at the antiderivative function, plug in the endpoint, plug in the start point. That number is exactly the same as the area number you get from the limit of the area construction. That is the fundamental theorem of calculus. Let's show it. Illustrate with this simple example to start before we actually prove it. So I want to do the integral of 1 plus x from 0 to 1. Sketch what that looks like so I can see the area I'm talking about. XY plane, y is 1 plus x. So that's my y of x function, 1 plus x. 0 to 1. And let me do 3 elements. So 3 rectangles. Label my partition points. I'll pick midpoints to choose for my height, because that's more accurate. So there's my height. There's my height. There's my height. Step 3, add up the rectangles. So there's my first rectangle, height times base, height times base, and height times base. Notice the special geometry here. These two triangles are exactly the same, over and under count. So this approximation is exact. So I'm dividing into 3 pieces, so 1/3, half of that is 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. This would be approximately equal, but because of the special geometry, the area under the curve is exactly the same as the rectangle area. So in this case, it's equal. Plug in my height times my base. Height times my base. Height times my base. Factor out the 1/3. Add together my fractions. 7, 6. Combine my fractions. Reduce. So there's my area under the curve. Now I'm going to do the antiderivative. Antiderivative of 1x and 1/2 x squared. Derivative of x is 1, so antiderivative of 1 is x. Plug in my endpoint and my start point. The c's will always cancel, so a lot of times we'll just not put them in. And it's the same area. Let's prove this thing. Instead of full generality, I'll just use numbers. Instead of a to b, let's say 0 to 1, just to kind of keep things simpler. So here's the statement of the fundamental theorem. I'm going to rephrase this in a different way. So capital Y is the antiderivative of little y. That means the derivative goes the other direction. Capital Y prime is little y. So in my integral, I can replace little y with capital Y prime. This is the statement we'll prove. Before we do, we need to refresh our memory about the mean value theorem. Mean value theorem is a statement on slopes. We look at a graph of a function, pick any 2 points on that function, calculate the slope of the line segment that connects those points. Slope, rise over run. Now, take that line segment and shift it till it's tangent. At that point, when I plug it in the slope function, it's the same number. And there's a mean value theorem that rise is slope times run, where I'm evaluating the slope at some unknown point in between A and B. This is what we're going to be using. Now on to the heart of the result. The area under y prime gives y. set up my integral, which is the limit of my Riemann sums. Do my Riemann sum, n rectangles, drive n to infinity. That's my integral. So we'll look at a small value of n, say 3, to illustrate how the construction is going to go. Step 1, put up my partition. Step 2, choosing a point for each element, I'm going to do this way. I'm going to plug the ends of the element into capital Y. Look at the line segment that connects those 2 points. Its slope is the slope function somewhere in between by the mean value theorem. That's how I'll choose my evaluation point. Yx1 minus yx0 is my Riemann sum rectangle. Height times base. For the second element, I just need to plug in one more point into capital Y, draw that line segment. Its slope, rise over run, is equal to the derivative at some point in between. That's how I'll choose for my evaluation point for the second element. Yx2 minus yx1 is my Riemann sum rectangle. And the same for the third element and so on. Expanding the summation notation, I'm adding 3 terms. I equals 1, I equals 2, I equals 3. Mean value theorem, mean value theorem, mean value theorem. The x1 terms cancel, the x2 terms cancel, and all I'm left with is the endpoints of the interval. This is true for any capital N. The construction is the same, so as I drive n to infinity, it's still true.